All right, Ms. Treadway here. We are doing our notes on section 9.3 today, the altitude on hypotenuse theorems. And this one can get a little tricky, but if you just look at it the way I'm going to explain it, it should be pretty straightforward. So first of all, a reminder of what an altitude is. We did learn this in the fall. An altitude is perpendicular to the opposite side. So in this triangle here, triangle ABC, segment CD would be an altitude because it is perpendicular to AB. Now what we're going to use here is using that I now have three triangles. I have the smaller one, the medium one, and the bigger one all together. And all three of these triangles are similar to each other by our angle-angle similarity. And using that information, we can write all three of these relationships here as proportions to find missing sides of our triangle. But that all looks a little overwhelming. So let's talk about how exactly those theorems come to be. So if I take my really big triangle and I split this up into the three separate ones, I've got triangle ACD, I've got triangle BCD, and my largest triangle with all three, BAC. So I just took each of those three triangles and I've drawn them down here so that we can understand what's going on here a little bit better. And I'm just going to go ahead and number these 1, 2, and 3 because that'll be a little bit easier when we're talking about each triangle. So starting with the relationships between triangles 1 and 3. This angle A and A are the same angle, and then they're both right triangles. So triangle 1 and triangle 3 are similar by our angle-angle similarity. So if I'm talking about triangle 1 and 3, triangle ABC is similar to ACD. And because of that, I know that the segment AB corresponds to AC, BC corresponds to CD, and AC corresponds to DA. Now, if you'll notice, in my relationships here, I have segment AC in there twice. It's the same segment. So using that information, I'm going to set up a proportion. So AB to AC would be equivalent, that ratio, of AC to DA, because those are our corresponding sides. Now, because I have AC here twice, that's the same thing as AC squared is equivalent to AB times AD if I were to use my cross multiplication. Now, if I'm looking at what those segments are on my triangle here, AC is the length of B, so B squared is equivalent to AB is the segment C, and AD is X. So if I knew at least two of those values on my triangle, I could find the missing one. So that's the relationship between triangle 1 and our bigger triangle. So ACD, this triangle here is triangle 1, and my biggest triangle. Now let's talk about triangles 2 and 3. They both have this angle B that they share, so those are congruent to each other. And again, we have right triangles, so they are similar by our angle-angle similarity. And so we can say that triangle ABC is similar to triangle CBD. And again, I'm going to go ahead and list my corresponding sides. AB corresponds to CB, CB corresponds to BD, and CA corresponds to CD. Now again, I have two repeating segments. I have CB here twice. So using the same thing I did with 1 and 2, I'm going to set up a proportion using these four segments. So AB corresponds to CB, and that ratio would be equivalent to CB over DB. And again, if I do my cross multiplication, I'll get that CB squared is equal to AB times DB. And then looking at my figure here, the segment AB is the length C, DB is the length Y, and CB is A. So A squared is equal to C times Y. And again, if I knew two of those lengths, I could find the missing one. So that was our second triangle, that one on the right. Now let's talk about triangles 1 and 2. They are also similar to each other by our similarity. They both share this angle C, and they're both right triangles. So, if I'm talking about triangle 1 and triangle 2, triangle ACD is similar to triangle CBD, which means AC corresponds to CB, CD corresponds to BD, and AD corresponds to CD. And again, I do have a repeating segment, and that's our CD for these two corresponding sides. So once again, I can write my proportion. CD to BD is equivalent, to AD over CD. And if I do my cross multiplication, I'm running out of room, so I'm going to go down here. CD squared is equal to AD times BD. And again, looking at my diagram, I'm going to fill in those values. We know that CD is H, so H squared is equal to AD is X, and BD is Y. So that is how we derive all of these relationships and proportions, but that can still be a little tricky to digest. Looking at the summary of our formulas is a little bit of an easier way to understand exactly how we're going to use these theorems. So again, I've got my large triangle with my two smaller triangles inside. My altitude is the one that's perpendicular to the opposite side. And what this altitude does is it splits my hypotenuse into parts. So you could call them part 1 and part 2. And then I have the legs of my triangle. So the hypotenuse is the one across from the right angle, and I've got my two legs. So using this diagram in my formulas, the relationship is part over leg is equal to leg over hypotenuse. And so if I were to solve that out with cross multiplication, that would be that leg squared is equal to part times whole. Now when we're doing it this way, we're using the same leg. So whichever leg we're wanting to find, you would say leg over the part of that triangle. So if I'm talking about the triangle on the left side, the left leg, I would have to use the left part. If I was talking about the leg for the right triangle, I would use the right part. And then again, the whole is the hypotenuse length. And then the second formula is part over altitude is equal to altitude over part. We only have one altitude, so the altitude is the same here, and you would use both parts. Okay, and in this case, it doesn't matter which one comes first, but you would use both parts of our triangle. So let's see this in action. So on this first one here, we want to know what formula can be used to find x in the triangle below. And we're going to actually go ahead and solve it as well. So first of all, let's identify if we're looking for a leg or an altitude here. X goes from the vertex to the opposite side, and we're going to assume that it's perpendicular. So that would make x an altitude. So I'm looking for an altitude. So the formula I want to use is the one that involves my altitude in both parts. Well, I do know both parts of the triangle. For reference, this would be a leg and this would be a leg, and this whole length would be my hypotenuse. So I'm going to use my formula of altitude squared is equal to part times part. So my altitude is x, and then my two parts are 2 and 9, and again, it doesn't matter what order. So x squared is equal to 18, which means that x is the square root of 18, and I can simplify that. So x is equivalent to 3 square roots of 2. Okay. Now on the second example, we want to find y, and y is a leg. Remember, this part here is my altitude. This is my leg. This is the other leg. I have part, and then this length C here is my hypotenuse. So I want to use my formula that involves leg, and that would be leg squared is equal to part times whole. So my leg length is y, so y squared is equal to, now remember which part we use matters here. Because I'm using the leg from this side of the triangle, I need to use the part from that side of the triangle as well. So the part I'm going to use is 15. And then my hypotenuse I have to calculate. I have to calculate 8 plus 15, which is 23. So y squared is equal to 15 times 23, which is 345. And so y is equivalent to the square root of 345. And that one, even though it's really big, does not simplify. And that is going to wrap it up for part 1 of our 9.3 notes.